In this video, I'd like to cover the basic concepts related to bolted connections for steel structures. And I'll refer you to your textbook for this section. The textbook's actually pretty good. Most of what I'll say is included in there. I'll try to do it in more of a condensed summary here, but beginning on page 495, you can read about bolted connections in there. Let me give you a quick preview of some of the key highlights. I've already pre-prepped some of this diagram, so rather than you watching me write it out, there's a lot of equations on this particular section. So I've written all those out. I thought about just referring you to the textbook for those equations, but I have found that it's useful for students to hear me walk through the equations and what all the pieces are. Seems to and also draw a few diagrams. Seems to help the students understand and comprehend what they're actually checking a little bit better. So with bolts for steel structures, there's two basic types. There's common bolts, and typically these are designated ASTM A307. If you look at the top of a bolt, sometimes you'll see A307 stamped on there. That would be a common bolt. These types of bolts are used for lightweight structures. So by lightweight steel structures, I mean structures that simply don't carry a large amount of loading. And the key with these types of bolts is that we just tighten them snug. If you've ever had a common bolt and you've gone beyond snug, you have a very high likelihood of actually shearing the bolt and damaging it. Well, damaging it and then shearing it to where it's not useful, and you got to get another replacement bolt. And if it's holding your structure together and it breaks, that's a bad thing. So for our larger steel structures, we use a category of bolts called a high strength bolt. And as you would guess, the strength of high strength bolts actually is significantly larger than just a common bolt, meaning you're paying for better, higher quality material with the bolt. These tend to be ASTM A325 or I should say and probably, but I'll leave it as or, A490 bolts. Those are the two standard types that you'll see with them. And two keys with this as well. The first one is we tighten the bolt significantly. So I'm going to actually draw on the bolt right here. I'm going to draw a arrow up, and likewise there would then be an arrow working downward, and I'm going to put a capital T on here. Rather than force, usually we use a P for point load or F for force, I'm actually going to put a capital T for tension on here, because we tend to tighten these beyond snug in such a way that we develop a tensile force within the bolt. In other words, we're stretching the bolt, for lack of a better way to say that. Now, we don't actually want to stretch it in the sense that it's moving, but we're applying that tensile force and creating that. Now, if the bolt is being put in tension, that means that the two plates are being compressed together. And if you remember from your physics class, this is one of the few times I do reference the physics class in here, you end up developing a large frictional component along the interface of the two plates that's there. Now, this is where we apply the point load right here. And if I've got this frictional component that develops at the interface right there, because the bolt is in tension, the friction actually acts as an additional force helping hold the connection together. And that's the key with high strength bolts. We pull it so tight that we develop friction to help hold the connection together. Now, one other thing that I want you to note here, if this thing was going to shear, we'll actually show it in the next one a little bit better, but it would actually shear right across the bolt right there if the bolt was going to shear. And so one quick key that I want to notate while I'm on this diagram is that the threads are below the shear interface. And what that does is it allows us to have the force being carried across the maximum diameter of the bolt. Obviously, if you're going across the threads, then you've got less material carrying that load. And so common bolts a lot of times will go all the way up to the top. If you go to Home Depot, sometimes you'll see that. For high strength bolts, you'll inevitably see that the threads are supposed to be below the shear surface so that we're maximizing the material there. All right. Now, when we're doing a bolted connection, there's about 4 or 5 major things that we need to look at as far as failure is concerned, or rather potential failure, things that we need to design for. So we're going to scroll down here. The first one that we want to look at is what we call bolt shear. And I just barely drew that one on there. Again, we're looking at a load that's putting a shear force on this particular bolt. And it would, I'll exaggerate it a little bit better here, it would shear right there through the middle of the bolt. And notice that there's only one interface where this shear failure could occur, and so we call this a single shear condition. On the other diagram that I've got already pre-drawn here, if I had a load P right here, and we'd have to have a half load P on that plate and a half load P on that plate. The point being I've got a full point load in each direction right here. This load actually now gets spread across 2 shear surfaces, and so we end up with the condition we would note as double shear. Now, the failure mechanism here is based on the strength of the bolt. And so if we were looking at our 2 equations here, you'll notice it's the same equation other than there's this 2 that shows up on the double shear side. But as far as the actual keys in this equation, we're looking at the load being carried across the area. That's how we define shear stress. So this is the bolt cross-sectional area. And the N simply signifies the number of bolts that may be included in that connection. So we're literally counting up how much surface area of bolts has to break before the connection breaks. I'm not going to draw the same I'm not going to identify each of the same ones in writing on the right side, but note that the same parameters remain in effect, other than I will label the 2 for the double shear condition. You'll recall that the FV was the actual shear stress that develops in the bolt. Little f for actual and V for shear. And the F sub V is simply the shear stress of the bolt itself. How much shear capacity that particular bolt can handle. One interesting thing about doing bolt shear is the textbook also has these equations embedded into a table. So if you go to table 10.1 on page 504, then you can actually skip using these equations and find your values there. And what you'd have to do is select the bolt type, the hole type. There's different types of holes that can be used. The shear type, whether you're using single shear or double shear, and then finally the bolt diameter. And you'll see that in the table there. All right, so that's failure mechanism number 1, actually shearing through the bolt. Failure mechanism number 2 is a phenomenon that we call bearing. And bearing has to do with the contact surface. You'll note within the 2 bolt holes of this plate, now I'm only showing the top plate here, we would be considering bearing of just this plate. And if there were bolts going through these holes right here, and we had a point load P acting this way on the plate, then the bolts would actually be pushed up against the edges of the cylinder. And I've tried to highlight that with the ghost shadows of what it would look like inside. The diagram to the far left actually shows, I'll go ahead and highlight it in red. We're looking at the surface area of the cylinder of the actual bolt hole. And so if we go look at the equations now, the contact surface area, A sub P, is simply the number of bolts, the plate thickness, and that was a really sloppy S, plate thickness, and the bolt diameter. This ends up being essentially, I notated as the cylinder of the hole, but it's really the surface area, contact surface area of the bolt diameter that would be touching that cylinder. Now, as far as calculating the bearing stress, we see that in these equations right down here. We've got the little cursive F for actual, P for bearing stress. I'm not sure why it's lowercase p for bearing stress, but that's how the book notates it. Then we've got P for our load, point load. We already defined the contact surface area above. And then the allowable bearing stress is the capital F sub P. And oddly enough, they define this with another equation, which is here. It's equal to 1.2 times the capital F sub U, which is the ultimate strength. And if we go, one of the few times we've actually used table 5.1, refer you back to table 5.1. We use table 5.2 all the time, but table 5.1 was introduced with the material properties. You'll recall just really quickly that when the curve comes up and then it comes out across and then it goes down, when it peaks right up here, that's the ultimate stress. And of course it comes down and then ruptures out here. So it's right after it goes into that strain hardening range. For 36 KSI still, the F sub U is equal to 58 KSI, and for 50 KSI still, the ultimate strength is equal to 65 KSI. You'll notice that that's significantly higher than the yield stress, and that is because we've entered that strain hardening range, and we want to work with that. Now, one other quick thing to note here is if you go to table 10.2, page 505, I highlighted that in black, even though I usually use green. We'll circle it and bubble it in green, just so you know this. There's also another table where you can grab the values for bearing stress and not actually have to use the equation. All right, the next two failure mechanisms have to do with failure of the plate itself. And the first one is a gross plate failure. And this one occurs if the plate, I'm showing a top view, a plan view of a connection here. If the plate was to break out, I'll jag it just so you can see it a little bit better, but this would be the failure plane that would go through a gross plate failure. And over here I've drawn a cross section of what the plate would look like, and notice that it's simply the thickness of the material, and this ends up being the width of the plate itself. So thickness of the plate times the width of the plate gives us our gross area. Of course, you can see that in the equation over here. I've got that notated. So this is plate width, this is plate thickness, and of course we know this is a tensile type stress, a tension stress, and so here's our actual tensile stress for the gross plate failure. Here's our load divided by the gross area, which was defined above. All that has to be equal or less than, technically you don't want to be equal, but less than the allowable tensile stress. And notice again they define this with another equation. The allowable tensile stress is equal to 60% of the yield stress. So for 36 KSI still, that would be 60% of 36 KSI. The net plate failure is nearly identical, except that what we're doing, instead of failing out along the plate, we're failing, whoops, wrong color. We're failing the plate along the location where we've drilled out some of our material for the bolts. And so in the cross section here that I've drawn to the far left, you'll notice that again I've got the thickness of the plate right here, I've got the width of the plate right here, but I essentially have to subtract out the diameter of the material where it failed, where it was drilled out for the bolts. So in this diagram right here, I'm showing, I'm not sure why they changed from a W to a B here, but this one is the plate width. I'm trying to follow the same notation the book does, and they seem to tweak it up every once in a while. This one's the thickness, so that's essentially the gross area, but we have to subtract out that material that's removed. So there's the number of bolt holes that's there. And note, this one is not the diameter of the bolt itself, but rather the diameter of a bolt hole. So we'll just call it the diameter of a standard hole. And we should note, the book indicates that it's typically a 1/16 of an inch larger than a bolt diameter. So we'll just quickly notate that D equals bolt diameter plus 1/16 of an inch. Right there. All right. Now, if we scroll down just a little bit further here, again, when we're calculating our actual stress along that particular failure plane, right there we again have the load divided by the area that we defined. This has to be equal to the tensile stress. Whoops. Sorry, thing jumped. Again, this is tensile stress, but in this case, this is the tensile stress for the gross. Sorry, I said that wrong. Tensile stress for the net, in which case we define that to be 50% of the ultimate stress. And we previously defined what ultimate stress was for you. All right, the final one I'm actually not going to give you any equations for, but I do just want to notate the importance of the spacing that's utilized. If we apply some point loads here on these two different plates, and we ended up tearing out where the bolt holes were. Let's say the bolt holes were too close to the edge. You could actually tear out this chunk right here, and part of the connection would fail. We avoid this type of a failure by using minimum spacing. And what we'll do is just give you a generic rule of thumb for now, and note that you should follow these guidelines as notated in plans and specs typically. Mostly what we want to do is just define the terminology for you though. I've drawn here what the different distances are. This is the distance of the bolt hole to the edge. usually measured from center line to the edge. The spacing between the bolt holes along the front face or in the perpendicular direction is called the gauge, and the spacing along the material or the parallel plane is called the pitch. And the preferable minimum pitch and gauge spacing is equal to minimum pitch and gauge spacing is equal to 3 times the diameter of the bolt. And so there's your rough rule of thumb. More often than not, as long as you're 3 times the diameter of the bolt or greater away, then your pitching and your gauge will be at an acceptable level. Edge distance is determined, it's similar. You'll note here that we've drawn them approximately the same, but it's a function of actually calculating a tensile failure for the net material. So there you go. There's your major concepts. You can read about these a little bit further in the textbook. You can see the equations as well in the textbook if you weren't taking notes and walking through. But I wanted to have this video available in case you wanted to hear me talk through the equations. In the next video, we'll do an example of a steel bolted connection, and I'll go through the equations, but rather than spend a lot of time talking about what those equations are, I'll just pretty much be noting the equations and plugging values in. So use this video for the reference to understand what the equations are and how they work.